bunch of spins. Hamiltonian was and we had this probability distribution over the spins, which was proportional to a Gaussian. And we determined that we wanted to compute the expectation value, the averaged over the disorder. So this is average over disorder. Of the free energy. This is hard. So what we did was we replicate the system n times. And then say that f bar is equal to minus 1 over beta, limit as n goes to 0 of d by dn z bar to the n. So we replicated our system n times. We did we took n to be an integer, and at the very end we took the limit n to 0 after taking a derivative. And we were led to a free energy. I'm going to write it here because I'm going to use it later. So this is before taking n to 0. We were led to a free energy that, well, we were led to a z bar to the n, which in the end was just an integral over one matrix. And then we had our action. Okay. So that's what we derived last time. And then we took the ansatz that all of our replicas, okay, so we're replicating our system n times, we're integrating over the disorder, but nothing distinguishes between my replicas. So the label 1, 2, 3, 4, 5, it's just a label. So the guess should be that this overlap, and let me remind you that the definition of QAB was 1 over n, sum over I, sigma I A, sigma I B. And this was a thermo average. So the effective theory of this disordered spin model, so we have some disordered coupling between our spins, and in the end we derived an effective theory that couples the replicas together. And we're trying to understand the physics of this replica coupling. What kind of physics does it give us? And remember, one thing we said was that if this thing had a ferromagnetic transition, then this state of sigma would be polarized in some direction, the direction of the magnetization of the system. And if you replicated the system twice, then this overlap would be very strong. It would be 1. But here we don't have a reason to believe that these things should be overlapping with each other, but we're going to entertain the possibility that they do. So we took this guess that the overlap matrix was diagonal. The 1 has to do with the spherical constraint. And then we're just going to assume that there's no distinguishing thing about any of the replicas. All replicas are created equal. And so we're just going to study what the expectation of this u. And the basic guess is that this u should be 0. System is completely disordered. There's nothing that suggests that any system should look like any other system. If you looked at the state of the system, it's going to be completely frustrated. There's no way to satisfy all the bonds. So we expect that this u should be very small. Okay. So we plug this guy in, and we derived in the limit n to 0 the replica symmetric free energy. And I'm going to divide by n. I don't remember if I divided by n last class, but I should have divided by n, because there's a big n over here. And we derived that this quantity was, sorry, no little n here. So now that we have a free energy, and it depends only on one variable, u, and this u, remember it's an overlap, so it's a cosine, so it's valued in -1 and 1. So now what do we need to do with this free energy? What do we always do with a free energy? Yes, yes. Thank you. That's still there. Didn't go away. So what do we want to do with this free energy? Minimize it. How do we minimize it? It's just a calculus problem. Very good. Yeah, we just take the derivative of f bar rs. Rs, remember, means? Replica symmetric. Very good. Replica symmetric. Divided by u. And we get, it's pretty easy. It's just beta j squared over 2 p, u to p minus 1, minus u over 1 minus u squared equals 0. So we want to solve this equation. And now note that since p is positive, u equals 0 is always a solution. So that's great. So that makes sense, right? We expect that no overlap in this system. It's good when you derive some equation. There were a lot of steps in this derivation. I know it was a tiring lecture last time. I apologize for that. But at the end of the day, now we have an equation. Now we have to just solve it. And it's good to see that when you try to analyze it, you get something that matches with your intuition. If you found something that didn't match with your intuition, then that would be a problem. Okay. So let's massage this equation. We want to. So u equals 0 is always a solution, but it's not the only solution. So let's rewrite this equation. So So I'm just going to rewrite it. It's not doing anything, any trickery. And remember, u is between -1 and 1. Okay, so what does this tell us? And of course, I've divided out the u equals 0 solution. So this is only for the u not equal to 0 solutions. So when t is very large, and u is between -1 and 1, it's impossible to satisfy this equation. Right, so for t very big, there's no way to satisfy this expression, because you need something built out of some quantity that's taken between -1 and 1 to equal something very big. It's hard to do that. But as you crank t down, all of a sudden new solutions start to appear. So let's analyze this equation graphically. So the way that this equation looks is, I'm going to pick a p to plot it, but the features are pretty agnostic on p, so I don't remember what p I'm picking. This is off the top of my head. So this equation looks like this, and this is u is equal to 0. This is u, and this is 1. And I guess this is -1. And this is for t bigger than, much bigger than j. So there's no solutions in the range. And then when I start to lower the temperature, this bump starts to rise. And all of a sudden, so this is t going down, t decreasing. And then all of a sudden there's a solution. And when this plot hits this 0, you get a new solution. And you get a solution where u is not equal to 0. And then above this special temperature, you have two solutions. And then which one should I pick? Any guess what is the reasonable guess? Yeah, you want to minimize f. That's one criterion. Anything else? You should ensure that f is convex. We'll talk about that. All right. What happens to this solution as you lower temperature? Does it go up or go down? Goes up. What about this solution? Goes down. So one solution, as I'm lowering the temperature, has less correlations with the other systems. And one solution, as I lower the temperature, correlates more on average with the other systems. So actually, this solution is spurious. It's weird. It behaves in a kind of unphysical way. So what we're finding is that as you lower the temperature, there is one solution that says that on average, this thing gets stuck, but it's stuck in a way where if I compute the variance over my replicas, there is some correlation. The spins themselves don't orient in any direction, but it tells you that the replicas want to somehow agree a little bit, and agree more and more as you lower the temperature. And it turns out that this guy, indeed, is the smaller free energy. Okay, so this is weird. This is weird because there's no order in my system. I have a system that's totally disordered. And what I found is that even though the system doesn't magnetize itself, so it doesn't pick up its own one-point function for anything, any correlation that you would expect, like spontaneous magnetization that I can measure for the system itself, somehow the thing that tells me that I'm in some new phase is that if I somehow imagine replicating my system and asking if on average the two systems look close or not, as I, consider the whole landscape of disorder, then that is the thing that tells me that I have a new thermodynamic phase. So it's a bizarre diagnostic for a new phase. So you should absolutely be confused by that. So are there any questions about what the meaning of this is? This is just, I'm plotting this. Because we want to satisfy this thing equals to 0. So I'm just looking at where it crosses 0. That's all I'm doing. I'm just plotting the left-hand side, and I have found a solution when this thing crosses 0. That's all. Is that what you're asking? No, it's the y. So y equals this as a function of u. And when y is 0, then I've satisfied the equation.
U equal to 0.
No, but sorry. You're right. I'm writing this. I've taken this to the other side. What I'm plotting is this.
So what is in the vertical line?
This. I've divided out the u equals 0 solution.
It's U and what?
With different temperatures.
No, this is u.
With different temperatures.
No, I know.
Okay, let me call this f of u.
Okay.
And I want f of u equals 0.
I also have a doubt on the graph. You always draw like a vertical line on the left?
Yeah, this
kind of vertical line?
This guy?
Yeah. That line never passed through to -1?
No, it does sometimes, but it depends on what p is. That solution is not.
It's not important at the end.
It's never the right one.
Okay.
I drew it that way to ignore it. But you're right.
Can you give a physical interpretation of the replica trick? Why you use this? Why this could tell you something about the n equal 1 physical problem?
Yeah. Well, we really want to take n equals to 0. It's kind of weird because we started with one system and now we want to take 0 systems. But it's because we want to compute the log. So what it's telling you is that actually the disorder average theory has an interesting state space. And the state space is labeled by this kind of auxiliary variable which measures these like how close they are, right? This This is kind of a distance measure in space, in phase space. And what this is telling you is that it's a very complicated free energy landscape, but on average, you have some amount of closeness. And the existence of a non-zero overlap is telling us that somehow the system has some kind of closeness. But it turns out, so before we can get to the final punchline, it turns out that this solution is actually never the right solution. So we've minimized the free energy. Well, yeah, we've minimized the free energy, but one thing that we have to check is whether or not this solution is stable under perturbations. So let me sketch how you would do that. I'm not going to go through it because the details are very complicated and yeah, not very illuminating, but I will sketch how you do it. Okay? So the way that we do it, is it okay if I erase this board? So sketch. So how do we check whether or not this solution is stable? So let's call this QRS, replica symmetric. And what you want to do is you want to go to your original action and imagine writing QAB is equal to QABRS on the correct solution. So, well, I don't know, star plus a little delta Q. And you want to expand to quadratic order in this. So what you find is that the fluctuation part of the action will look something like this. And then the question is, what is the spectrum of this operator? What are the eigenvalues of M? And if it has negative eigenvalues, then you found the wrong saddle. That this is unstable. And it turns out that on this solution right here, M has negative eigenvalues. On all the solutions. This one, all of them have negative eigenvalues. So back to the drawing board. So we're getting somewhere. So we solved this equation. The equation is telling us that there wants to be some kind of overlap. But it turns out that this background is unstable. So we need to think hard. Oh, and I forgot to tell you your exercise. Your exercise 7, what, 7? 6. Exercise 6 is show that for p equals 2, no new solutions. No u not equal to 0 solutions. You should be able to determine that from the equation that I erased. Very, very easy. Okay. So back to the drawing board. Back to the drawing board. So what do we do?
Tarek, small question. Do you have a measure of like how negative, in the sense of it could be long-lived or something?
Do I have a sense of how negative?
Or I mean, if that's important, if not, it's okay.
Yeah, the eigenvalues depend on this u being non-zero. I don't remember what they look like. I can give you a reference if you want to see what the eigenvalues look like.
Yeah. So you've been talking about the replica symmetry. Does that mean we can also have like other things in the matrix?
Yeah. Very good. Back to the drawing board is what is there left to do? What's the only thing that seems like it would be the obvious thing to do now that I have found something that is lower in free energy but is unstable? Of course, we could say, oh, you know, there is just none of these solutions are real. But actually, if you just at low temperatures study the thermodynamics of this thing with u equals to 0, you'll derive some kind of nonsense stuff. You'll see that the thermodynamic system has negative entropy at low temperatures. So really, it doesn't want to be in the state with u equals to 0. But this is the incorrect saddle. So we have to go back to this guy and try to find the correct stable saddle. Okay, this looks like a little bit like a hard problem, because first we have to find the correct stable saddle for our n bigger than 1, and then take n less than 1. Okay. So as Aditya mentioned, what we want to do is consider potentially breaking this replica symmetry. And now you should be really confused. How am I allowed to do that? I'm going to take the number of replicas to 0 anyway. Like, what's going on? But it turns out that this is the like only place that you can fiddle. So I'll erase here. So the next best guess. So one thing that's nice about this this guess, this replica symmetric guess, is that it's completely insensitive. You're allowed to permute replica indices, and the matrix doesn't change, right? The eigenvalues won't change. It'll be completely insensitive to relabeling the replicas. So this is a very symmetric solution. Turns out it's the wrong solution. So the next best thing that we can do is imagine breaking this replica symmetry, breaking the permutation symmetry among the replicas down to a smaller permutation symmetry. And so the next guess is to break the permutation symmetry. So we still have 1s along the diagonal, because that's a requirement by the spherical constraint. Breaking the replica symmetry down to a subgroup means you pick some m by m part of your n by n matrix, and you allow that to have an off diagonal. I'm going to call that U again. But you make sure to do that all along the block. And then I'm going to have another value over here. So here, now I've broken my permutations only to work inside a block of size m. And then outside of the block, I can permute freely, but I have this kind of structure. And this is called one-step replica symmetry breaking. So that's our next guess. And we turn the crank again. We need to plug this into our action, derive the equations of motion. So remember, we wrote down the action over here very conveniently. So let's now analyze this solution. So what do I need in order to be able to write down that action on this solution? I need to be able to take the log of this matrix. So what's the best way to do that? I need the eigenvalues. OK, so now you're at exercise 7. Show that the eigenvalues are lambda 1 is 1 minus u, and it has degeneracy 1 minus n over m times n. And then the next eigenvalue, lambda 2, is 1 minus u plus m times u minus s. And that has degeneracy n over m minus 1. And then finally, lambda 3, 1 minus u plus m times u minus s plus ns with degeneracy 1. All right. Now they'll add up to n.
So the fact that these things happens and the replicas talk to each other, is it related to the fact that when you're introducing the replicas, you're still keeping only one average interaction over the whole thing instead of averaging the whole replica by themselves? That's the...
Yeah, it's the doing the integral over the j's after taking the log.
Yeah, but I mean, so you're adding sigma IA
Yes,
while keeping j I1 blah 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 without an index A.
correct.
If you add that index A, then it
There
will
would be
like
no
nothing.
coupling of the replicas at all. You would never couple them. It was very important that every replica received the same coupling J. Otherwise, this trick wouldn't work. Okay. Let's do the exercise all together. We need to count some stuff. We're summing over the whole matrix. From this term right here, QAB to the P, summed over all the indices. So we need it's audience participation time, and not hangman. Okay, how many ones in that matrix? I heard it. N. How many U's? How many times in the small matrix? Okay, this is an m by m matrix, and U is on the off diagonal. How many elements of off diagonal are in an m by m matrix? M squared minus m. How many off diagonal matrices are there of these? Yeah, very good. So there's n over m times m minus 1 times m. So we can delete this. How many times does s appear? This is the easiest one now that we've computed these guys. Yeah, n squared minus the sum of these two. So we have n squared minus n minus n m minus 1. So, sorry, this cancels with this. And I get n times n minus m. Okay. And now we can just plug this into here. The easy part is upon us. The hard part is past us. So long as you do exercise 7. Don't forget. Very important. Okay, so let's plug it in. So we now have integral over u from minus 1 to 1. So this is z bar to the n. Integral over s, also from minus 1 to 1. And we have to sum over m's. Because m is some number that divides n cleanly. We have to sum over m. And then so we have n times n times 1 plus u to the p times m minus 1 plus s to the p times n minus m. That's this term. U to the p times n minus 1. 1 to the p is 1. S to the p times n minus m. So I pulled out an n. Okay, and now I just have to take the logs of those lambdas. So I can pull out an n everywhere. One minus u plus m times u minus s. And then there's one that's 1 over 2n. It's the only one that doesn't have an n dependence. Log of 1 minus u plus m times u minus s plus us. And what's the last step? These, yeah, same u. That's the one step. It's because we want to break the permutation symmetry, but we don't want to completely break it. What's the last step to derive our equations of motion? We have to take a derivative and then take n to 0. I guess this is poor board management. Which one would you prefer I erase? This board or this board? This one. Okay. Sorry for not going linearly. In Arabic, we write from right to left, so Okay. So F1 RSB divided by n. Remember, I take the derivative of this guy with respect to n, and then I set n to 0. So it's like taking the derivative of what's in the exponent. So I get minus 1 over 2 beta, beta j squared over 2, 1 minus u to the p plus m times u to the p minus s to the p plus s times 1 minus u plus m u minus s, 1 minus 1 over m, log 1 minus u, plus 1 over m, log of 1 minus u, plus m times u minus s. Okay. Oof. And if you want, a nice check that we did everything correctly is if I set u equals s, the dependence on m drops out, and I get the replica symmetric free energy from before. That's a nice check. You can do that with your eyes. I think it's pretty obvious. Okay. And now we want to solve this equation, and something interesting happened. We broke replica symmetry by introducing a u and an s, but we got a new parameter in our free energy for free, and that's this parameter m. And we know u and s are an overlap. They're from -1 to 1. But what are we supposed to do with m? What is the physical space that m lives in? Remember, before we took n to 0, m had to divide n. But now we've taken n to 0. So what do we do? We need a guess. Any guesses? It's not obvious, so it's okay if you don't get it. But let's see if anybody has any ideas. All right. So these u's and s's, they're a measure of distance on the space of states, right? So let's think about what the probability density would be on that space of states. So imagine I wanted to define a probability density on these overlaps. I'm going to call them Q in an average sense. Well, one way to think about that is to think about summing over A and B delta Q minus QAB. And of course, I need to normalize so that this thing is equal to 1. So let's say sum over A greater than B, and 2 times n minus 1. Because we don't care about this 1, so we can just focus on the top half of this matrix. Okay. Well, you guys know exactly. You guys just did the exercise, so what is this probability density equal to? So we're gonna do hangman, but in a special way. I'm gonna have a delta Q minus U and plus delta Q minus S. And I want you to tell me what the coefficients are. See if you're awake after lunch. You've already solved this problem. Almost. I did A greater than B. Divide by 2. So we can take out this 2, put a 1 here. So we have n times m minus 1 over here, and n times n minus m over here. So that's our probability density. And nice, we can delete this n. And actually, we can compute this in the limit n goes to 0. Actually, this limit exists. So in the limit as n goes to 0, so as n goes to 0, what do I get? This becomes minus 1. So I get 1 minus m q minus u plus m q minus s. Okay, who can tell me now what I should value m in? What's the most important thing a probability distribution should be? Yeah, both of those things are correct, yeah. Both normalized and positive. Lucky for us, this is normalized. What about positive? Is it positive if m is 2? Is it positive if m is 3? Yeah, very good. So now we have to take m between 0 and 1. So m, as n goes to 0, to make sense of this system, we need to take m to be a continuous number now between 0 and 1. Okay. So we're getting there. So, okay. Quick recap.
Hi. M divided n.
Correct.
Right? And you take n to 0
Correct.
and keep m fixed.
Correct.
And the assumption that m divided n doesn't matter now?
If that were the case, then we would not really get any sensible equations in the n to 0 limit.
Ah, yeah. Okay. Okay.
So we have to extend m. So all of this, okay. Let me give you a quick recap. Yeah, just to explain what's going on. We introduced these replicas in order to take this log. The log is the thing that we want. We're not powerful enough to do that, so we need to introduce these replicas in order to do it. We can only introduce replicas in an integer number of ways, but we need to somehow continue those to n equals to 0. And we need to develop some heuristic tools that give us sensible answers in that limit. Of course, all of this is something that would make a mathematician cry if they were watching these lectures. Sorry, YouTube. But what we're doing is a physics derivation. It turns out that this physics derivation is correct. In fact, there's a mathematician named Talleyrand who has analyzed systems such as these, and he has shown, using epsilons and deltas and the most sophisticated analysis you can imagine, that indeed studying these equations gives you the free energy minimum correctly if you were able to take the log. This bounds the free energy minimum above and below. It's like everything that a mathematician dreams of. But doing that is very difficult, so we have to use our sloppy physics tricks. Yeah, if I take m to 0, if I take m to 0, you would see like this probability over the overlaps would mean that I don't really have this s. I would have introduced this s, but it's not really there if I take m to 0. I need to take m finite in between 0 and 1 to really keep this s in the limit n to 0. Correct. Now it is, yeah. That's the trick. That's the trick. It's, okay, the only thing I can tell you is if you want to be more convinced, then there's a nice graduate textbook in mathematics that goes through this with the epsilons and the deltas. I'm not capable of reading it. It scares me, but maybe you're much more brave than I am, and that's the place to look. It's by this guy Talleyrand. I don't remember the name of the book, but if you just look up the author, I think that's the one he wrote. Yeah, he recently got the Abel Prize. That's right. So he's a very well-respected mathematician. Okay, so that's the aside. Now we have a free energy. This is our, where did I write it? This is our free energy. And now we want to analyze it just like we analyzed the previous case, the replica symmetric case.
Can I bug you one more time on the limit? Seems surprising that here, if you take m to 0, you sort of lose all the u's, whereas there, you just get the u eigenvalue.
Yeah, yeah. Funny how that works. It doesn't really make sense to take m to 0 first, right? Like, first of all, the only thing that you can take here is m to 1. That's the best that you can do. You can't reach m equals 0 on that side. You can imagine taking m to 0 here. So if you take m to 1, you just get s. You're back at the replica symmetric situation. And then you see it's all fine and good. If you take m to 0, you can't. There's no way to understand it from that picture. Okay. So now we want to analyze the equations. And we have to keep in mind that, that m is between 0 and 1. So S was what we were calling U before. So let's study that guy. So if I just compute the equation, I get something that looks like this. So this should look a lot like the U equation that we were studying before. And here you see that S equals 0 is always a solution. In fact, the correct analysis of this theory is that S never wants to be anything but 0. Actually, that was the mistake we made with the replica symmetric solution. S always wants to be 0. That's exactly what we were saying before. If you pick any two random configurations and you look at their state vector and you measure the distance between any random other system that you built using the same disorder, then they should be completely uncorrelated. This is what you expect absolutely for a disordered system. And finally, we found something more sensible, that the overlap is 0. Okay, so that's good. So S is always 0. S equals 0 is always a solution, and it's the right one, always, at all temperatures. That's great. That's what we want. The replica symmetric solution was a little bit crazy. We assumed that there could be a non-zero overlap between any systems picked. Like if we replicated them and tried to check whether or not they agreed, we would find that they always agreed a little bit. That's too strong. Here we're seeing that a vast majority of the configurations just are completely uncorrelated. Much more sensible.
Tarek, a question. When you say that S wants to be 0, what we should do in order to prove it is to fluctuate, find that it's stable. You're skipping this, but that is your statement.
That is my statement.
Thank you very much.
Yeah, I can't show you all of the steps. I know I'm showing you a lot of steps, and it's tiring, but I'm just skipping some here. So yeah, S always wants to be 0. The correct analysis of this system is if you compute the solution, free energy is minimized at S equals to 0, and it's a stable solution. So we're going to set S to 0 from now on. So actually our matrix is going to look like this. It's much more reasonable. What the existence of this U is telling us, so if we find something that's not equal to 0, is that there's still a non-trivial state space, so the states aren't completely decorrelated. There are some states that are close, but they're not all free energy states. There's just some small proportion of the free energy states where the system wants to agree. It gets stuck in some configuration, and it's roughly close to some other sets of configurations, but by and large, the system is completely disordered. So the 0 is telling you that there's never any situation where all of the time, if you pick any two systems and you measure their overlap, they're going to agree. Okay? So what we want to find is whether or not this U can be non-zero. And if we find that the U can be non-zero, that'll be evidence of a new phase. In particular, if we can show that it's a stable solution. Okay. So let's study these equations numerically. Oh, sorry, I didn't tell you what the equations were. So the other equations are so this one is m minus 1 so I'm setting u to s to 0 now. So here you see again, U equals 0 is a solution to this equation. It's good. That's the high temperature solution. That's what we expect. We also have to vary with respect to m, and we get okay. So we have two equations and two unknowns, and we need to solve them. It's not an easy equation, easy set of equations to solve, but you can just plot it, graph it, whatever. You want to find the zeros. And let's draw some plots. So no surprise, at high temperatures, the only solution is U equals 0, m completely unspecified. If you just set U equals to 0 here, then you satisfy both these equations. And m, it can be whatever, it doesn't matter, any number between 0 and 1. It won't affect the free energy. The free energy dependence on m will drop out if U and S is 0. So the high temperature phase will be the diagonal replica matrix. Everything is as you expect. System is completely disordered. There's no, any two states you pick from an ensemble will just not look like each other. This would be true in a ferromagnet, so this is not like, this should not come as any surprise. But as you lower the temperature, you can satisfy these equations. And if you stare hard enough, you might notice that this equation is satisfied if I set m to 1. It's not really surprising. It's m minus 1 out front. And it turns out that m equals to 1 exactly at the critical temperature. M equals to 1 exactly at the critical temperature. Because at m equals to 1, that's telling you that the system is basically in the phase where all the overlaps are 0. You haven't started populating states where the overlap is not 0. Remember, this S is 0. So we'll just plot this equation at m equals to 1. So now it's just a function of u. So I'm going to call this again f of u. It's f of u comma m, but I'm going to set m equals to 1. And now let me plot f of u comma 1 as a function of u. And of course, there's a solution at u equals 0. So this is for t much, much greater than the critical temperature. As you lower t, you get a feature that looks like that. And then the critical temperature, so this is u equals to 1. And the critical temperature, this is t less than Tc, t greater than Tc, but not much, much greater. The critical temperature, you get something like that. And you all of a sudden get a non-zero u. So this system is pretty interesting. So just let's recap again. We had this disorder. We wanted to do this log thing. We had to introduce replicas. And then we developed a theory, an effective theory of the replicas. And it turns out that the way to characterize the space of solutions was to look for non-trivial overlaps in the space of these configurations, these replica overlaps. And the thing that characterizes the low temperature phase is one where the system, remember, has no spontaneous magnetization, but the configuration space breaks up into pockets. So if you were to pick any two copies of the system up at random and compare them, on average, you would get one of two numbers. You would get either 0 or you would get this number u. And that's also kind of weird, right? You have a dirty system. If you are very capable of measuring the state of the system, it's just completely dirty, right? And you average over the couplings in some reasonable way, you would only get two answers. The state space would split up into two wells. One where the two systems were completely orthogonal to each other, and one where they have an overlap that's not 0, but fixed, and you would agree on what that overlap is over any subset of these replicas. So the claim is and maybe you'll disagree with this or not. The claim is that U and M are order parameters for the glass transition. I should mention, for this model, this solution is stable. Yes? Yeah, no, so M equals to 1 only at the critical temperature. In general, as you go below the critical temperature, M goes less than 1. It's only at the critical temperature that M equals to 1. M and U have a dependence on the temperature. So at Tc, M is 1, and U is some finite value. Okay.
Below TC, do you have an interpretation of M as how long are these correlations or something?
Yeah, what is the interpretation of M? So if you look at this, the interpretation of M is kind of a measure of how big the proportion is of states that are far from each other versus close to each other. There's another interpretation of M. Maybe I'll discuss it in the last lecture, but I don't know if it's a little bit hard to explain, so you may forgive me for not making an attempt. I don't know if I would do it justice, but you see, M is the answer to a question. You want to minimize the free energy, and you find M on the free energy minimum. But, of course, spin glass people are very creative, and you can relax the requirement that you minimize the system with respect to M. In fact, you can cook up ways of making M a parameter that you can tune, just like an external magnetic field. One way to do that is to imagine not doing the replica trick, but first replicating your system by hand, and then doing the replica trick. And M is the number of replicas that you have. So then it becomes a thermodynamic parameter that you can tune, and it has a You know, just like taking a derivative with respect to the inverse temperature gives you the average energy, taking a derivative with respect to m gives you something else. I'm not going to say what it is. Yes.
Yeah. So I'm kind of lost. I mean, I understand that U and M are order parameters for all of this, but I don't understand.
Why this is a glass.
Yeah.
So let's go back to, I drew this picture early this morning. We have a cup of water, and you know, these things have their dipoles, they point in various directions. And remember, if you lower the temperature to the critical temperature for forming ice, then this thing all of a sudden polarizes all the dipoles. So the system becomes ordered in the ice phase. If you cool it very quickly, we say it becomes a glass. That's another phase. But the intrinsic dipole moment of the water is 0 on average over the system. But nevertheless, we want something to characterize this phase. And the claim that I'm making is the way that you should think about that is to take a snapshot of your water at very low temperatures in the glass phase, take another snapshot, compare them, and if there's an overlap, you're in a glass phase. It's a very strange overlap. It's a very strange order parameter. We'll discuss next time another way to think about it, but really this order parameter is telling you that you shouldn't take it too literally, that this is measuring some overlap of configurations of your system, because of course at the end it's an average overlap, right? The real way to do it is to compute a thermodynamic average and then average over all of your distribution of couplings, right? And then only at that stage, so if you were able to do that, would you see these overlaps? It's not like something that you would see if you didn't do this average over the couplings. So it's really hard to imagine how to measure this U in real life. Kind of almost an impossible task. What this U is really telling you is that your configuration space, as complicated as it is, because of course we have a completely disordered coupling amongst our spins, what this U is telling you is that the configuration space, despite appearances in the beginning that it's completely random and very complicated, actually has some order to it. It tells you that there is a way to think about a structure to this very complex free energy landscape. But the thing that, the variable that tells you about that structure is not one that you would expect, and it's not an obvious one if you hadn't started by trying to solve this model to begin with. It's a big question, how do you measure something like this?
Tarek, question. Above the critical temperature, I now regain the 3 solutions, the 0 and 2 other, and the same story goes,
Yes.
right?
Yes. I mean, of course, you have to worry about M not being 0 above the critical temperature, but what you get is something like this. And this one, the overlap increases with decreasing temperature. So it's the one that makes more sense. And this one, the overlap decreases with decreasing temperature. It's counterintuitive, and it turns out that that's not a good free energy minimum.
Thanks.
Hello. Would we have the magnetization to be 0?
Yeah. 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 So you can argue that from here. In particular, if P is even, so all of this stuff is agnostic on P. But if P is even, then the system has a Z2 symmetry, flip the spin. And so you expect that for any state with plus spin, there's a minus spin, and the expectation value for the magnetization should be 0. But really, the expectation of it being 0 is the fact that this thing, there's nothing that wants it to order. There's no coupling that pushes it to an ordered phase. Other questions?
So below the critical temperature, do you know how M behaves as you change the temperature, if it ever reaches 0, for example?
Yeah. No, indeed. Oh, of course. Sorry, guys, technical difficulties. Thank you. We're back, baby. Indeed, yeah. So M indeed goes to 0 as you lower the temperature. It decreases from 1. So now you have these equations. They're very explicit. You can just study them. And you can just look and see what happens to M and U as a function of temperature. It's completely within your hands now. What's surprising about this model is that you don't have to continue. After you've put in this one-step replica symmetry breaking ansatz, that's it. You're done. This is the free energy minimum at low temperatures. That's very nice. The first model that was solved of this type was the following. Something called the Sherrington-Kirkpatrick model. This one is or maybe all spins. So the S are either plus or minus 1. So this is like an Ising model. And it's just 2 body interaction, and this J is again disordered. And this model maybe looks easier. It's only 2 body, but the fact that you have the spins taking values in plus or minus 1 makes this model much more difficult to study. And it turns out that the solution to this model was discovered by Parisi. And the free energy minimum at low temperatures is an infinite step replica symmetry breaking solution. So you have to imagine doing this. It's one step, and then that one is not the right free energy minimum, and then you have to imagine then breaking up the M by M matrix into a smaller M2 by M2 bunch of blocks, and that one is still not the free energy minimum, and then you do that again infinite times. So there's a continuum of M's and a continuum of U's and S's, and that's the solution to this model, which also has the same kind of order parameter, but this one is easier to present. So that's why I decided to present this one rather than this one. Okay, I'm kind of done, I guess. I could go on, but I think you guys are tired, and this is a good stopping point, so yeah. The upshot is we have new order parameters, these U and M. They're kind of weird from the perspective of the original thermodynamic system we were studying. And it's hard to square in our little hearts whether or not these are actual order parameters and whether or not they're actually measurable in any way. So over the next 2 lectures, I'm going to try to convince you that there's an imprint of these variables if you consider the dynamics of this model. So all we've done so far is study the statics of this spin model. Now we're going to let the spins depend on time, and we're going to see whether or not we can get some grasp of this U and this M in the time dependence. That's it.
Okay, questions? I have one question. 2 questions. Can I be rude a little bit?
You can be rude, yeah.
Excellent. You have shown me that this computation does not yield the same result as option 1.
Uh-huh.
Is there a way to see that it is the correct answer for option 2? Because it does not look exactly like the same computation.
No, yeah. For that, you again have to go to this book.
Okay, okay. And there is the proof that...
There's the proof, yeah.
Okay.
That if you were to do first the log and then the disorder average, then you would find the same thing. Yeah, yeah.
The same thing as the replica trick result.
Yes, yes.
Okay, okay. Authority principle, I can live with that.
Yeah, yeah. No, it's
no, it's okay. It's okay.
not expected at all. I agree.
Okay, thanks.
Is it really right to call them order parameter? Are we, as we go past the phase, do we still have disorder, right? Or is it like a quasi order? What is like?
Yeah. They're order parameters in the sense that they change from being 0 to non-zero as you cross the critical temperature. But do they? So this is an argument that people have in the community, I guess. Not being an expert, I'm not going to say whether or not there's an agreement. But I think that roughly some people believe this is an order parameter, and some people believe it's not.
All right, thank you.
I have one. So you showed me now that you have a free energy and that it has a critical point and that it's stable. So what's out of equilibrium?
Yeah. Yeah. Out of equilibrium, yeah, so this is a subtle point. So out of equilibrium means that really the system is never so this is a very complicated Hamiltonian. If you were to prepare your system and cool, no matter what, the phase space of this system is very complicated. And it's basically impossible to find the minimum of the free energy. So even though there is a free energy minimum, if you try to reach it by some cooling process, it's not going to happen. But the thing that does happen is that the system will get stuck, and the system being stuck is captured by these overlaps. Yeah. So this is kind of telling you that this is telling you about the system being stuck while it's looking for the free energy minimum. So I used equilibrium techniques. I never used out of equilibrium techniques for a system that will never equilibrate. And that's what the replica trip kind of buys you.
You have some notion of tunneling to the right solution and how much
Tunneling.
time it takes?
Tunneling is, so for tunneling you need dynamics. Here there's no tunneling, but we will turn on dynamics and then maybe we can discuss that, yeah.
More questions? Okay, then we thank Tarek again.